Section 14.5, Reaction Mechanisms. A balanced chemical equation does not tell us much about how a reaction actually takes place. In many cases, the balanced equation is simply the sum of a series of steps. Consider the following hypothetical example. In the first step of a reaction, a molecule of reactant A combines with a molecule of reactant B to form a molecule of C. A plus B arrow C. In the second step, the molecule of C combines with another molecule of B to produce D. C plus B arrow D. The overall balanced equation is the sum of these two equations. Step 1, A plus B arrow C. Step 2, C plus B arrow D. Overall, A plus 2B arrow D. The sequence of steps that sum to give the overall reaction is called the reaction mechanism. A reaction mechanism is comparable to the route traveled during a trip, whereas the overall balanced chemical equation specifies only the origin and the destination. Notice that in the two steps, the C is canceled because it appears on the reactant and the product side. And notice that the B's are additive. A B in one step plus a B in a second step becomes two B's. For a specific example of a reaction mechanism, we consider the reaction between nitric acid and oxygen. 2NO gas plus O2 gas yields 2NO2 gas. We know that NO2 does not form as the result of a single collision between two NO molecules and one O2 molecule because N2O2 is detected during the course of the reaction. We can envision the reaction taking place via the following two steps. 2NO gas, arrow N2O2 gas. N2O2 gas plus O2 gas, arrow 2NO2 gas. In the first step, two NO molecules collide to form an N2O2 molecule. This is followed by the step in which N2O2 and O2 combine to give two molecules of NO2. The net chemical equation, which represents the overall change, is given by the sum of the first and second steps. Step 1, NO plus NO, arrow N2O2. Step 2, N2O2 plus O2, arrow 2NO2. Overall reaction, 2NO2 gas plus O2 gas, arrow 2NO2 gas. Species such as N2O2 and C in the hypothetical equation up above are called intermediates because they appear in the mechanism of the reaction but not in the overall balanced equation. An intermediate is produced in an early step in the reaction and consumed in a later step. Elementary reactions. Each step in a reaction mechanism represents an elementary reaction, one that occurs in a single collision of the reactant molecules. The molecularity of an elementary reaction is essentially the number of reactant molecules involved in the collision. Elementary reactions may be unimolecular, one reactant molecule, bimolecular, two reactant molecules, or termolecular, three reactant molecules. These molecules may be of the same or different types. Each of the elementary steps in the formation of NO2 from NO and O2 is bimolecular, because there are two reactant molecules in each step. Likewise, each of the steps in the hypothetical A plus 2B arrow D reaction is bimolecular. The overall equation has three reactant molecules. Because it is not an elementary reaction, though, we do not classify it as a termolecular reaction. Rather, it is the combination of two bimolecular reactions, step 1 and 2. Student note, termolecular reactions actually are quite rare, simply because the simultaneous encounter of three molecules is far less likely than that of two molecules. Yes, three molecules colliding at the same time is a rare event. Knowing the steps of a reaction enables us to deduce the rate law. Suppose we have the following elementary reaction, A arrow products. Because there is only one molecule present, this is a unimolecular reaction. It follows that the larger the number of A molecules present, the faster the rate of formation. Thus, the rate of a unimolecular reaction is directly proportional to the concentration of A. The reaction is first order in A. Rate equals K times the concentration of A. For a bimolecular elementary reaction involving A and B molecules, A plus B arrow products, the rate of product formation depends on how frequently A and B collide, which in turn depends on the concentrations of A and B. Thus, we can express the rate as rate equals K times the concentration of A times the concentration of B. Therefore, this is a second-order reaction. Similarly, for a bimolecular elementary reaction of the type A plus A arrow products, or 2A arrow products, the rate becomes rate equals K times the concentration of A squared, which is also a second-order reaction. The preceding examples showed that the reaction order for each reactant in an elementary reaction is equal to the stoichiometric coefficient in the chemical equation for that step. In general, we cannot tell just by looking at the balanced equation whether the reaction occurs as shown or in a series of steps. This determination must be made using data obtained experimentally. So just as a reminder, the elementary step, if you look at the balanced equation, the elementary step, the rate law for the elementary step is proportional to the coefficient raised up as an exponent in that particular reactant, but not for the overall reaction, just the elementary steps. Rate determining step. In a reaction mechanism consisting of more than one elementary step, the rate law for the overall process is given by the rate determining step, which is the slowest step in the sequence. An analogy for a process in which there is a rate determining step is the amount of time required to buy stamps at the post office when there is a long line of customers. The process consists of several steps: waiting in line, requesting the stamps, receiving the stamps, paying for the stamps. At a time when the line is very long, the amount of time spent waiting in line, step 1, largely determines how much time overall process takes. To study the reaction mechanisms, we first do a series of experiments to establish initial rates at various reactant concentrations. We then analyze the data to determine the rate constant and overall order of the reaction, and we write the rate law. Finally, we propose a plausible mechanism for the reaction in terms of logical elementary steps. The steps of the proposed mechanism must satisfy two requirements. 1, the sum of the elementary reactions must be the overall balanced equation for the reaction. 2, the rate determining step must have the same rate law as that determined from the experimental data. The decomposition of hydrogen peroxide can be facilitated by iodide ions, figure 14.16. The overall reaction is 2H2O aqueous, arrow, 2H2O liquid plus O2 gas. By experiment, we can find the rate law to be rate equals K times the concentration of H2O2 times the concentration of I minus. Thus, the reaction is first order with respect to both H2O2 and I minus. Figure 14.16. The decomposition of hydrogen peroxide is catalyzed by the addition of an iodide salt. Some of the iodide ions are oxidized to molecular iodine, which then reacts with iodide ions to form the brown triiodide ion. The decomposition of H2O2 is not an elementary reaction because it does not occur in a single step. If it did, the reaction would be second order in H2O2 as a result of the collision of two H2O2 molecules. What's more, the iodide ion, which is not even part of the overall equation, would not appear in the rate law expression. How do we reconcile these facts? First, we can account for the observed rate law by assuming that the reaction takes place in two separate elementary steps, each of which is bimolecular. Step 1, H2O2 plus I minus, arrow, H2O plus IO minus. with a K1 above the arrow. Step 2, H2O2 plus IO minus, arrow H2O plus O2 plus I minus with a K2 above the arrow. If we further assume that step 1 is the rate determining step, then the rate of reaction can be determined from the first step alone. Rate equals K1 times the concentration of H2O2 times the concentration of I minus, where K1 equals K. The IO minus ion is an intermediate because it is produced in the first step and consumed in the second step. It does not appear in the overall balanced equation. The I minus ion, that's called iodide, does not appear in the overall equation, but it is consumed in the first step and then produced in the second step. In other words, it is present at the start of the reaction and it is present at the end. If iodide ion is a catalyst, the iodide ion is a catalyst, and its function is to speed up the reaction. Catalysts are discussed in greater detail in section 14.6. Figure 14.17 shows the potential energy profile for a reaction like the decomposition of H2O2. The first step, which is rate determining step, has a larger activation energy than the second step. The intermediate, although stable enough to be observed, reacts quickly to form the products. Its existence is only fleeting. So this is the potential, figure 14.4, potential energy profile for a two-step reaction in which the first step is rate determining. R and P represent reactants and products respectively. Potential energy versus reaction progress. Reaction, step 1, there's activation energy for step 1. Then it lowers in energy to form an intermediate. Then there is a second step, which has a second activation energy, which is smaller than the first, and then it forms the products. The first step has the largest activation energy. Therefore, it is the rate limiting step or the rate determining step. Experimental support for reaction mechanisms. When you propose a mechanism based on experimental rate data, and your mechanism satisfies the previously laid out requirements, 1, the individual steps must sum to the correct overall equation, and 2, the rate law of the rate determining step must be the same as the experimentally determined rate law. You can say that the proposed mechanism is plausible, not that it is necessarily correct. Plausible means possible, but doesn't mean it is correct. It is not possible to prove that a mechanism is correct using rate data alone. To determine whether or not a proposed reaction mechanism is actually correct, we must conduct other experiments. In the case of hydrogen peroxide decomposition, we might try to detect the presence of the IO negative ions. If we can detect them, it will support the proposed mechanism. Similarly, for the hydrogen iodide reaction, detection of iodine atoms would lend support to the proposed two-step mechanism. For example, I2 dissociates into atoms when it is irradiated with visible light. Thus, we might predict that the formation of HI from H2 and I2 would speed up the intensity of light, would speed up as the intensity of light is increased, because that would increase the concentration of I atoms. Indeed, this is just what is observed. In one case, chemists wanted to know which CO bond is broken in the reaction between methyl acetate and water to better understand the reaction. There's two possibilities of bond breaking are, first one, the H2O is reacting with the CH3COOCH3, and what happens is the CH3 is broken off. In the second possibility, so in the first possibility, there's a bond breakage between the C and the O on the left, that's A. And then the second possibility, there's a bond breakage of the O and the C on the right of the molecule. Notice where that's occurring. To distinguish between schemes A and B, chemists used water containing the oxygen 18 isotope instead of ordinary water, which contains the oxygen 16 isotope. When the oxygen 18 water was used, only the acetic acid formed contained the O18. Thus, the reaction must have occurred via von Breaking scheme A, because the product formed via scheme B would have retained both of its original oxygen atoms and would contain no oxygen 18. Another example is photosynthesis, the process by which green plants produce glucose from carbon dioxide and water. 6CO2 plus 6H2O, arrow, C6H12O6 plus 6O2. A question that arose early in the studies of photosynthesis was whether the molecular oxygen produced came from the water, the carbon dioxide, or both. By using water containing only the oxygen 18 isotope, it was concluded that all the oxygen produced by photosynthesis came from the water and none came from the carbon dioxide, because the oxygen O2 produced contained only oxygen 18. These examples illustrate how creative chemists must be to study reaction mechanisms. Identifying plausible reaction mechanisms. In assessing the plausibility of a reaction mechanism, we apply the same two criteria that we use to propose a mechanism. 1. The individual steps, which are called elementary processes, must sum to the correct overall reaction. 2. The rate-determining step, the slow step, must give the same rate law as the experimentally determined rate law. Student note, recall that for an elementary process, the exponents in the rate law are simply the coefficients in the balanced equation. Consider the gas phase reaction of hydrogen with iodine monochloride to form hydrogen chloride and iodine. H2 plus 2ICl, arrow, 2HCl plus I2. The experimentally determined rate law for this reaction is rate equals K times the concentration of H2 times the concentration of ICl. We present 4 different proposed mechanisms. In mechanism 1, step 1, ICl plus ICl, arrow, I2 plus Cl2, slow. Step 2, Cl2 plus H2, arrow, 2HCl. The steps in mechanism 1 sum to the correct overall equation, or reaction, I should say. ICl plus ICl, arrow, I2 plus Cl2, Cl2 plus H2, arrows, 2HCl. The Cl2's cancel, so the sum is H2 plus 2ICl, arrow, 2HCl plus I2. However, the reaction law of the rate-determining step is rate equals K times ICl squared. Therefore, mechanism 1 is not plausible. Doesn't work. It meets criterion 1, but does not meet criterion 2. Mechanism 2, step 1, H2 plus ICl, arrow, HI plus HCl, slow. Step 2, ICl plus HCl, arrow, HI plus Cl2. The rate-determining step in mechanism 2 has the correct rate law. Rate equals K times H2 concentration times ICl concentration. However, the steps do not sum to the correct overall reaction. H2 plus ICl, arrow, HI plus HCl, slow. ICl plus HCl, arrow, HI plus Cl2. The HCl's cancel. The sum is H2 plus 2ICl, arrow, 2HI plus Cl2. Therefore, mechanism 2 is not plausible. It meets criterion 2, but does not meet criterion 1. Remember, the slow step has to give you the rate law that's consistent with the experimentally determined rate law. Mechanism 3, step 1, step 2, step 3. H2, arrow, 2H, which is slow. Step 2, ICl plus H, arrow, HCl plus I. Step 3, H plus I, arrow, HI. The rate law for the rate-determining step of mechanism 3, rate equals K times H2, is not correct. Furthermore, the steps do not sum to the correct overall reaction. H2, arrow, 2H, slow. ICl plus H, arrow, HCl plus I. H plus I, arrow, HI. Sum H2 plus ICl, arrow HCl plus HI. Therefore, mechanism 3 is not plausible. It meets neither criterion 1 nor criterion 2. Mechanism 4. Let's hope this one's right. Step 1, H2 plus ICl, arrow HCl plus HI, slow. Step 2, HI plus ICl, arrow HCl plus I2. The rate determining step in mechanism 4 has the correct rate law. Rate equals K times H2 concentration times ICl concentration. Furthermore, the steps in mechanism 4 sum to the correct overall reaction. H2 plus ICl, arrow HCl plus HI, slow. HI plus ICl, arrow HCl plus I2. The sum is H2 plus 2ICl, arrow 2HCl plus I2. Therefore, mechanism 4 is plausible. It meets both criteria. Sample 14.11. Sample problem 14.11 lets you practice determining if a proposed mechanism is plausible. So try that one, and try practice problem A and practice problem B. Mechanisms with a fast initial step. For first and second order reactions, it is reasonably straightforward to propose a plausible mechanism. We simply use the experimentally determined rate law to write the rate determining step as the first step, and then write one or more additional steps such that the appropriate species will cancel to give the correct overall equation. Sometimes, however, we will encounter a reaction with an experimentally determined rate law that suggests an unlikely scenario. For example, consider the gaseous reaction of nitric oxide with chlorine to produce nitrosyl chloride, 2NO gas plus Cl2 gas, arrow 2NOCl gas, for which the experimentally determined rate law is rate equals K times the concentration of NO squared times the concentration of Cl2. Note that the exponents in the rate law are the same as the coefficients in the balanced equation, making the reaction third order overall. Although one possibility is that the reaction is an elementary process, this would require the simultaneous collision of three molecules. As we noted earlier, such a termolecular reaction is unlikely. A more reasonable mechanism would be that one in which the fast first step is followed by a slower rate determining step. So this is different than the one we looked at before. This one, the second step is slow. The first step is fast. However, when we write the overall rate law using the equation for the rate determining step, which is step 2, as we have done previously, the resulting rate law, rate equals K2 times the concentration of NOCl times the concentration of NO, includes the concentration of an intermediate NOCl2. Although this rate law is correct for the proposed mechanism, in this form it does not enable us to determine the plausibility of the mechanism by comparison to the experimentally determined rate law. To do this, we must derive a rate law in which only reactants from the overall equation appear. When the intermediate NOCl2 is not consumed by step 2 as fast as is produced in step 1, its concentration builds up, causing step 1 to happen in reverse. That is, NOCl2 reacts to produce NO and Cl2. This results in the establishment of a dynamic equilibrium, section 4.1, where the forward and reverse of step 1 are occurring at the same rate. We denote this by changing the single reaction arrow in step 1 to equilibrium arrow. NO gas plus Cl2 gas, double arrow, reversible arrow, NOCl2 gas. K1 in the top, K minus 1 on the bottom. We can write the rate laws for the forward and reverse of step 1, both elementary processes, as rate forward equals K1 times the concentration of NO times the concentration of Cl2. And rate reverse equals K minus 1 times concentration of NOCl2, where K1 and K minus 1 are the individual rate constants for the forward and reverse processes, respectively. Because the two rates are equal, we can write K1 times the concentration of NO times the concentration of Cl2 equals K minus 1 times the concentration of NaCl2. Rearranging to solve for the concentration of NaCl2 gives K1 over K minus 1 times concentration of NO times concentration of Cl2 equals concentration of NaCl2. When we substitute the result into the original rate law for the concentration of NaCl2, we get rate equals K2 times concentration of NaCl2 times concentration of NO equals K2 times K1 divided by K minus 1 times concentration of NO squared times concentration of Cl2, which agrees with the experimentally determined rate law, which is rate equals K times NO, concentration of NO squared times concentration of Cl2, where K is equal to K2 times K1 over K minus 1. Sample problem 14.12 lets you practice relating the experimentally determined rate law to a reaction mechanism in which a fast first step is followed by a slower rate determining step. Sample problem 14.12, try that. Also try practice problem A, practice problem B. Try checkpoints for section 14.5, reaction mechanism, 14.5.1, 14.5.2, 14.5.3, and 14.5.4.